today, and he'll continue his lectures on graphical linear algebra now.
Okay, thanks very much. So I'll just quickly go through, I'll give you a quick reminder of what we talked about yesterday. So we started off discussing just the basic theory of string diagrams, how we understand string diagrams, at least for the purposes of these two lectures. And then we introduced several of these symmetric monodal theories, and we kind of built up from basic, and we added more and more complexity. So we started off actually with just monoids and comonoids, and I claimed that the symmetric monodal theory of commutative monoids gave us functions. It's the same as, it's isomorphic to the proper of functions. And then we introduced bimonoids and argued that it's the theory of natural number matrices. We introduced the antipode, and we developed this theory of Hopf monoids, which gave us integer matrices. And then finally, we discussed this theory of linear relations, which is the theory of interacting Hopf monoids, which again sort of added another layer of complexity, right? So then we had sort of Hopf monoids interacting with Hopf monoids the other way. And I think there were already some questions yesterday about sort of where is this all coming from, right? Where are these equations coming from? And I think sort of this topic that I'm going to be talking about next, which is distributive laws, answers some of these questions, like where do these equations come from? So let's get started. So I'll just give you a reminder of what this theory of interacting Hopf monoids looks like. So we had the Hopf monoid going one way, a Hopf monoid going the other way, and these extra equations which told us how these two Hopf monoid structures interact. So we identified these Frobenius equations, these funny looking equations that tell you how these two different cups and caps interact, and these equations for scalars. So I claimed, we didn't actually prove this yesterday, that the symmetric monodal theory generated by this data is isomorphic to this prop of linear relations over the rationals. Okay, so I want to give you an argument why this is true, and to do that we'll need to talk about distributive laws of props. Okay, so there's a really nice paper by Steve Lack called Composing Props, where a lot of these ideas come from, and we've really sort of taken Steve's work and we've used it to develop this theory of interacting Hopf monoids. And what is it all about? So first of all, it's a variant of distributive laws of monads, which perhaps some people have heard about. And it's a little bit weird, right? Because what do props have to do with monads? So that's the first question. That's the first natural question that arises. Well, it turns out that since monads can be considered in any two category, which is this beautiful work by Ross Street from the 70s, formal theory of monads, actually, and this is the really weird point, a category is the same thing as a monad in span of sets. And this is I mean, the first time you see this, it's a bit weird, right? It's a weird statement. So I've got a slide on this. So hopefully, if you haven't seen this before, you have to kind of do a little bit of mental gymnastics to get around this concept. And then, strict monodal categories is the same thing as monads in span mon, the category of monoids. And there are some small technical complications for props because of symmetries. I don't want to get too technical in this talk, so we're going to skip over that, and I just want to give you the idea of what's going on and how these distributive laws work and what do they give us. So first of all, let's try to understand this point about how categories can actually be the same thing as monads. Okay, so let's think about sort of this idea about, the theory of monads in the two category. What is a monad in span of sets? Okay, so this is actually a bicategory, and a one cell, so an arrow in this category is actually a span of functions. Okay, so this is an arrow, and the domain is the same as the codomain, which is what you'd expect of a monad, right? So a monad, sort of in the standard traditional sense, is an endofunctor, right? So it's the domain and the codomain are the same category. But here we have a span, right? So we have some set O and some set A. I gave these names on purpose because we're going to think of this set O as a set of objects and the set A as a set of arrows. And then this span here, these two arrows, these two functions, delta 0 and delta 1, they simply tell you, given an arrow, what is the domain and what is the codomain. Okay, so this is the basic sort of, let's say, the one cell part of the data that defines a monad. And now we have to give a multiplication. So first of all, a multiplication, the type, should be from this composed of itself back to itself. Okay? But in span, we compose by doing pullbacks. Right? So essentially, this is the object that you get. This is the guy in the middle of the span. One would compose this with itself. And it turns out, so what I need to do is I need to take the pullback of delta 0 of delta 1, and I get this set. And if you think about how pullbacks and set work, what this really is just pairs of all the arrows that can be composed. Right? So all this is saying is, give me all the pairs of arrow A1, A2, such that the codomain of A1 is the same as the domain of A2. And so the multiplication is of the type, composable arrows back to arrows. So we might as well just call it composition, right? This is something that takes two composable arrows and composes them. And then the type of the unit of the monad is something that's going to go from O. Why O? Well, because it's going to be the identity one cell on O, which is just the span of identity functions of O, right, back to A. And this, we think of this as just picking out the identity arrows for each object. And then you have all the laws associated with monads. So, for example, the multiplication is associative, and it works well with the units. And if you just translate all that data of a monad back to this setting, it turns out just to give you precisely the equations, the axioms of categories. Right, so composition in the category is associative, and we have identity arrows, and composition works as you expect with identities. Okay, so in this way, you can think of a category as really the same thing as a monad in this category of this bicategory of spans. So now I want to get to the point of why do we talk about distributive laws? Well, it's all about putting props together, right? So in the story we've seen so far, we've gone from sort of one theory to another by constructing the more complicated theory from the simpler theory, right? So it's all about sort of putting props together in interesting ways. And distributive laws are one way of doing this. Okay, so let's imagine that we have a green prop P. Okay, so a typical so this maybe is a symmetric monoid theory, maybe it's something else. But basically, we have objects with natural numbers, and we have some arrows, and we have the usual algebra, and then we have a purple prop Q. And then I want to ask the question: when can we make sense of something that I'm going to call P composed with Q? And what I mean by this is that in this prop, I want to think of every single arrow as something in P followed by something from Q. Okay, so this clearly won't make sense always, right? Because if I compose two such things, I'm going to get something not of the right shape, right? Because I'm going to get green followed by purple, followed by green, followed by purple. So really, one way to make this work, one way to make this P composed of Q, one way to give it the structure that's expected of a prop, is to have a way of turning things that look the wrong, that are sort of the wrong, that come the wrong way. So if we have Q first and P, if I can always turn something like this into something where I have green first and purple second, right? Because then in this situation, if I compose, then I just flip these using lambda, and I now have two greens and two purples, and that's okay. Okay, and obviously these things have to satisfy some extra conditions in order for this to make sense. And this is really, it turns out that these are the conditions that the distributive laws specify. So, I mean, it's not really important that we go through this in detail. I just want to give you a feel for what's going on. So this is sort of the standard definition of a distributive law of monads. So given monads TU, a distributive law is a two-cell of the type UT to TU. That's compatible with multiplication in units in T and U in the obvious way. And when I say in the obvious way, I mean, you know, these are the diagrams you'd write down if you started writing down diagrams, right? So essentially, these two diagrams tell you that this way of swapping is compatible with how you do composition in U. This diagram tells you that it's compatible with the way that composition works with T, or multiplication in T, and these two diagrams tell you that it's compatible with the units. And the important part here is that this gives a monad structure on TU. Okay, and since we know that monads are the same thing as categories, this goes back to this slide. You know, if I can show that lambda is actually a distributive law, then I can make this this formal thing, you know, P composed with Q, an actual prop, right? So let me give you some examples, because there are loads of examples of this happening. So first of all, we have the symmetric monoidal theory of spans. And as we saw, you know, the bicategory span of set has spans of functions as one cells, span morphisms as two cells, compositions by pullback, as we saw. And we can actually obtain a category from this bicategory by identifying isomorphic spans. Okay, and it turns out that, okay, so we kind of know already how to deal with functions with string diagrams, right? It's a function is, so we have a theory of functions, it's a theory of commutative monoids, right? So can we make sense, and a span, what is a span? Well, it's something of the form a function backwards followed by a function forwards. Right, so can we make sense of a prop that's of this form, right? So comonoid followed by monoid. Well, we can if we can find a way to always turn diagrams that look like this into diagrams that look like this. And it turns out that we do have such an operation, right? Because, I mean, a diagram of monoids is just a function. This is kind of a function going the other way. So this is, since this is a function sort of going like this and this is a function going like that, we can take the pullback and we obtain functions of the right shape again, right? So by sort of taking the pullback in the category of sets, we can obtain a distributive law. And it turns out that the universal property of pullbacks gives you all of the conditions that are expected of distributive laws. Okay, so I want to give you an example of this in action. So let's try and figure out one equation of this SMT of spans. Okay, in particular, we can consider this particular pullback diagram. So this is the unique function from the two-element set to the one-element set, and this one too. And as pictures in the theory of monoids, it's just this. It's just the multiplication, and here it's just the co-multiplication. So if I take the pullback, I just get 2 cross 2 with the projections. Okay, so let's draw the picture of this. I mean, as you would sort of, you know, when you're explaining this stuff to undergrads. So these are the elements of the product. This is the first projection. This is the second projection, and you can basically just write down immediately string diagrams for this, because we know that the string diagrams correspond to the graphs, you know, the diagrams of the functions. Okay, so this pullback diagram gives us an equation that should be satisfied in this SMT of spans. Okay, so this equation we've already seen, it's an equation of the theory of bimonoids. So in particular, did I not say this? So in particular, it turns out that all the other equations of bimonoids can be derived in the same way, and then you can make an argument, so like a completeness argument, that the equations of bimonoids suffice to generate all the pullbacks. Okay, so you don't need to consider, obviously there are infinitely many pullback diagrams you can draw, but it turns out that those particular equations of bimonoids are enough to generate them all, right, after a while. You don't need to consider any more pullbacks because you already have enough equations to sort of prove the equations that will arise from a pullback. And so in particular, we know that bimonoids is the same thing as matrices over natural numbers, and in fact it's also the same thing as spans of functions. Okay, this category of spans of functions. So it's a really interesting fact, and by looking at it from this point of view, it kind of demystifies where these equations come from, right? They come from a very canonical way in which the monoid structure interacts with the comonoid structure via the pullback construction. Okay? So these equations don't come out of thin air, they come out for some deeper reasons. And just for fun, we can also think about the SMT of Cospans. So Cospans now has one cell's cospans of functions, so now we're sort of going inside. Compositions by push-out. Again, push-out defines a distributive law, and actually it turns out, interestingly enough, that the theory that you get is the theory of strongly separable Frobenius monoids. So essentially, we get the Frobenius law here and this special strongly separable equation over here. Okay, I don't really want to spend too much time on this, but you can basically verify this. I mean, this equation comes from a particular push-out diagram, and so does this. Okay. I mean, if you're interested, I could do this offline for you. So again, this is one way of demystifying these equations. They come from particular universal construction. Okay, so let's now go to the main proof. Let's try to prove that this theory of interacting Hopf monoids is isomorphic to the prop of linear relations. So
can you say what linear relations are?
Yes. So the prop of linear relations we have as arrows from M to N. Subspaces of Q to the N times Q to the N, where Q is the rationals.
Subspaces and what's it? Linear subspaces.
Linear subspaces. And composition is relational composition. Okay, so the core of the proof is two different distributive laws. Okay, so it's a slight generalization of Lack's notion. It's got to do with, I told you that there were some technical complications about symmetries. Well, there are a little bit more technical complications here, but it's not very interesting. So I'm just going to skip over this. But the point is, the main technical point to realize here is that this category of matrices over the integers has both pullbacks and pushouts. Because this is due to a fact that we've already mentioned, that this category is equivalent to the category of free finite dimensional Z modules. And because Z is a principal ideal domain, the integers is a principal ideal domain, this category has pullbacks. This is a fairly standard, well-known result. And then, because this is a category of matrices, we have this transpose operation. So any limit we have, we also have the co-limit, because we just take the transpose of a matrix and turn everything around. Right, so the universal property, I mean, if you have a universal property for let's say, for limits, I just apply transpose everywhere, and now I have the co-limit. And so we get two different distributive laws of how mad Z can interact with mad Z op. Okay? And mad Z is the same thing, of course, as Hopf monoids. So we get two different ways that Hopf monoids interact with Hopf monoids going the other way, so to speak. Okay, so I want to, again, we could spend some time calculating some pullbacks and pushouts, but I just want to tell you, I'll just give you a very high-level overview of what happens. So first of all, spans of matrices, we obtain, let's call the symmetric monodal theory IR span. So we get some of the equations of what did I? Okay. So I meant to call this IH span. I don't know why I called it IR span. So let's just pretend it says IH span. So essentially, we get these equations, and we get these equations by considering pullbacks of matrices. Okay, and we calculate pullbacks of matrices essentially just by looking at the modules and calculating just like in sets. Okay, so all of these equations you can figure out by calculating particular pullbacks, just like we did when we obtained the equations of bimonoids by looking at pullbacks of functions. Okay, so the interesting thing to notice here is that we get some of the equations of interacting Hopf monoids, but not all of them. Okay, so we have scalars, so we have this one rule where P is a non-zero scalar, that when P meets another P and they sort of point into each other, then they are the identity. But we don't have the other one, where two P's point out. That's not in general equal to the identity for spans in this theory. And also we have the two Frobenius laws, but only sort of the black Frobenius has the special equation, and only the white Frobenius has this bone equation. We still have these two different ways of relating the cups and the caps. And we have these extra equations which are actually sort of theorems for interacting Hopf monoids, but we need to add them as sort of first-class equations for this theory. So it turns out that if you consider this theory here, that's actually isomorphic to spans of matrices. Okay, and it's one way that matrices interact with each other, and you get these equations via pullback. Now, for cospans of matrices, because of the way we calculate pushouts via transpose, we actually get all the same equations, but somehow reversed. Right? So we reverse everything and we recolor. It's very simple. So we get basically all the equations that we didn't have before. So the white structure, the white Frobenius now has the special equation. The black Frobenius structure now has this bone equation, and we get the other rule for scalars. And it turns out that this theory here is now isomorphic to cospans, and this is by calculating pushouts. So we have these two different ways that Hopf monoids interact with Hopf monoids. Okay, one via pullbacks and one via pushouts. And now the cute thing is that the theory of interacting Hopf monoids essentially arises as the gluing together of these two theories. Okay, and there's this cube construction that features in many of our papers that sort of explains this. So let me just explain how this works. So H here is the theory of Hopf monoids, and this prop here is the coproduct in the category of props, which essentially the way to think of this is just to throw in all the generators of Hopf monoids and all the equations of Hopf monoids, all the sort of reverse generators and reverse equations, but no other equations. Okay, so it's kind of the free theory on just what happens when you have Hopf monoids and reverse Hopf monoids, but they don't interact in any meaningful way. And of course, because we know that H is isomorphic to mat Z, we get this kind of vertical isomorphism here. Now there's a canonical way of mapping from this to the theory IH cospan and IH span, and sort of on the semantic level, remember that we were thinking of symmetric monodal theories as somehow as the syntax and these other kinds of props here as the semantics. And so basically you get these, you get this sort of the back faces of a cube in which all the vertical maps are isomorphisms of props. Okay, so now we fill in the front face. So here we get the front face by just doing pushouts in the category of props. So because all these things are symmetric monodal theories, for symmetric monodal theories the pushout is quite an easy operation to understand. What happens is all of these three have the same generators. Okay, so here we just obtain IH by just putting together all the equations, right? We add the equations for spans together with the equations of cospans. We get interacting Hopf monoids. And down here, this is not a very difficult proof that if I calculate this pushout of, so if I glue together spans and cospans, then I get linear relations. Okay, so we have two pushouts, we have back faces all being isomorphisms, and we get for free, just from the universal properties of this cube, that this map, this morphism of props from IH to linearel is an iso. So that's the proof, sort of what, you know, that this theory of interacting Hopf monads is really the same thing as linear relations. But we also get some nice corollaries from this proof. So in particular, we know from the proof that every diagram in the theory of interacting Hopf monads can be factorized in two ways. Okay, we can think of it as a span where A and B are matrices. So I've got this the wrong way. This is a cospan, this is a span. So we can think of it as a span, or we can think of it as a cospan, where A, B, and C and D are matrices. Or the diagrams in the theory of Hopf monads. And plus we get some extra things, basically because of the universal property of pullbacks and pushouts. So every mono in Mad Z satisfies this, and every epi in Mad Z satisfies this. Okay, so we're going to sort of come back to some of these properties and think about what they mean in this sort of a linear algebraic setting. So this brings us to the second topic for today, which is I wanted to sort of, you know, we've built up this this complicated symmetric monodal theory. I want to show you some one way of thinking about doing linear algebra in this theory. Okay, so let's redo linear algebra, but instead of the usual way of, you know, defining vector spaces, bases, dimensions, etc., we're just going to do linear algebra with string diagrams. So first of all, factorizations. As we saw on 2 slides ago, we know that every diagram can be factorized as a span or a cospan. Okay, now if we look at very special kinds of diagrams, the diagrams from k to 0, then those diagrams should be in one-to-one correspondence with subspaces of q to the k, right? So in particular, these two different factorizations give us two different ways one can think of linear spaces. And this is, of course, this is a well-known fact, but it's key to see this diagrammatically. So one can think of a linear space as the set of solutions of a list of homogeneous equations, or we can think of a linear space as all the possible linear combinations of a set of basis vectors. So let's have a look at some examples. Okay, so this is these are some examples of spaces as solutions of homogeneous equations. So let's assume that our space is a subspace of q to the 3. So we have 3 possible dimensions to work with. So we can consider the space where x plus y is equal to 0. So this is the corresponding string diagram. So this is x, this is y. We add x and y, and then equals to 0. We can compose it with the 0 going the other way. Right, and this diagram here is really saying x plus y is equal to 0, sort of in a in string diagrammatical form. And here the z, well, the z is free. The z can be anything. 2y minus z is equal to 0. Well, again, so we take y, we multiply by 2. We take z, we multiply by minus 1. We add up and we make sure that this is equal to 0 and x is free. So this again is a space, a subspace of q to the 3, and the elements here are precisely the space is precisely the one defined by this equation. So we can also sort of put these two equations together, and here we're essentially saying that everything in the space has to satisfy, every vector in the space has to satisfy both the equations. And the way this works is we essentially sort of put both of these diagrams together using the comonad structure. So here we're saying that x plus y is equal to 0, but also 2y minus z is equal to 0. Right? So what about spaces as a linear combination of basis vectors? Well, now we can think of, let's say, the basis vector 1, minus 1, 0, and we want to consider all the possible linear combinations of it. Well, all we can do with one vector is just multiply it by a scalar. Okay, so now we're kind of going the other way. Instead of here we're going from left to right, now we're going from right to left. So first of all, this final element z is always going to be 0. So we attach the 0 lollipop. This guy here is free. This is sort of where the a comes from. And now, whatever a is, in the first coordinate we're going to have it, and in the second coordinate we're going to have minus it. Okay, same thing, we can do a similar thing for, let's say, b0, 1, 2. So the first coordinate will be 0, the second coordinate will just be generated by this diagram. And now we can also consider the space generated by these two vectors, by these two basis vectors, and it's going to be the space here, right? Now we have sort of 2 degrees of freedom. We have the scalar A and the scalar B, and we use sort of the white structure now, the addition structure, to add up the different kinds of scalar multiplications of these basis vectors. So I'm using linear algebraic language, but as you can see, it's all string diagrams. And it shows off a kind of a nice duality that's inherent in this theory of interacting Hopf monoids. And in fact, this is really we know we have this factorization to cospans and spans, and if you think about it, all of these guys are cospans, right? So if you look at to the left of this dotted line, we have matrices going from left to right, and this is a matrix going from right to left, not a particularly interesting one, of course. And this can be said for all 3 of these. And here we have matrices going the other way, right? So here we have, to the left of the dividing line, we have a matrix going from right to left, and here we have a not very interesting matrix from left to right, etc. Okay, so we know that every string diagram in the theory of interacting Hopf monoids can be factorized in these 2 different ways. And it turns out that these 2 different factorizations actually tell us interesting things from the point of view of, let's say, classical linear algebra. So let's just do a little more linear algebra. So we can define sort of well-known things like image and kernel. So what's the kernel? Well, A is a matrix, and if we just compose the matrix with 0 going the wrong way, then we're essentially defining the space on this side where all the vectors that get multiplied by A have to be equal to 0. Right? So this is the string diagram that tells me the kernel of A. The string diagram for co-kernel of A is similar. The image is now we take A and we pre-compose it with the black lollipop, which essentially says everything. Okay, this again is a space. It's a space of it's a subspace of the codomain, and it's the image of A. And the co-image is similar. Okay, and these are again very standard, classical concepts of linear algebra, but we're looking at them really just from the point of view of string diagrams and using the language of string diagrams only, right? There's no, vector spaces, bases, whatever. It's just string diagrams. So let's try to prove just some very, very basic linear algebraic results that you find in the first few chapters of any linear algebra textbook. So we know that injective matrices are the same thing as the monos in Mad Z, so in particular they satisfy this property that if I pre-compose with F and G and it turns out that the 2 compositions are the same, then I know that already it must have been that F and G are the same. So in interacting Hopf monoids, A is injective if and only if this condition holds. Right, so I already told you that if it's injective, then this happens. And this is essentially because this diagram here is a pullback in Mad Z, and therefore the equations of interacting Hopf monoids are enough to prove all the pullbacks. And so this must already be provable in the theory. This is by the completeness argument, which I didn't prove completeness, by the way. I just sort of said that it's true. It's a bit complicated. I mean, it's not very complicated. It's basically doing linear algebra of string diagrams again. It relies on a decomposition called the Hermitian decomposition. The other way is just a very simple calculation. We just basically assume, well, so let's assume that FA is the same as GA, or we can compose with A going the other way, and we know that these guys cancel out, so we're just left with F and G. Okay, so this is a cute little characterization of injectivity of a matrix in this theory of string diagrams. And again, surjectivity, well, it's just the bizarre dagger of everything that we said. We don't really need to say anything more. So let's prove this very standard result, that A is injective if and only if the kernel of A is equal to 0. So the kernel of A is equal to 0, diagrammatically, well, this is the kernel of A, and this is 0. Right, so this is the statement kernel of A is equal to 0 using string diagrams. Okay, and again, it's not a very difficult proof. So we suppose that A is injective. We want to show that this holds. So this is already the case that in the theory of Hopf monoids, everything can come out of a 0, right? So in particular, we can kind of conjure up A going the other way from the 0. Now when A meets an A going the other way, they cancel out by injectivity, and we end up with just the 0. There's a 0 missing here, right? Now let's prove the other direction. So we want to assume that that this holds, and we want to prove that A is injective. So we want to prove that this diagram is equal to this diagram. Well, here we're doing some rewriting. Okay, so this is something that I should have defined. I actually defined it on the later slide, but I must have rearranged it without thinking. Okay, so this is just a little syntactic sugar for that. And this is the same thing going the other way. So we're basically using the fact that the cap and the cap, the black cap and the cap define a compact closed structure. So we can move things around like so. Well, we know that the black cap is the same thing as the white cap with an antipode. We can commute the A past the antipode, move it down, use the fact that the kernel of A is 0 to get rid of the A, and then rearrange everything back to the A. Okay, so here's a proof using just string diagrams of this very sort of classical result of linear algebra. And it's not particularly impressive, but I want to give you a taste of the kinds of things that one does. And then you have for free, immediately sort of the bizarro of the claim that A is surjective if and only if the image is the codomain. So the image being the codomain is just, of course, string diagrammatically saying that this is the case. And we don't have to really write a proof because it's the same proof, but just reflected with and recolored. Okay, using this bizarro dagger that I explained last time.
Can you prove the isomorphism theory, saying that the kernel of the co-kernel is the co-kernel of the kernel?
Yes, yeah, but it's a little bit more difficult because it relies on some factorization in the theory of Hopf monoids. So I'm not going to go through this, but I plan to get through all of this on the blog. So I won't show you everything today, but yes.
Yeah, sure, but I'm just wondering, you can do.
Yes, yeah, sure. I mean, in the end, we have the isomorphism, right? So this is a language that should be capable of doing everything. The question is, do we want to? I mean, I'm more interested in finding sort of nice string diagrammatic ways of doing things than just translating word for word, theorems from textbooks. I don't want to use, for example, bases and equations. I just want to use string diagrams. So here's one reasonably interesting thing one can say about invertible matrices. So A is an invertible inverse B precisely when A is equal as a string diagram to B going the other way. Again, this is kind of very simple to prove. So, so let's assume that A is invertible with inverse B. Then A is the same thing as A, and then the identity is the same thing as AB. And the A cancels out, and we're just left with B. So here we're using the fact that A is mono, but this easily follows from the fact that A is invertible. So let's now assume this thing here. So let's first of all prove that A is injective. Well, we can use the fact that the kernel of A is 0, or we can prove that the kernel of A is 0, and then we'll know that it's injective. So let's check this. So let's check what the kernel of A is. The kernel of A is this guy, but A is the same thing as B going the other way. And whenever I have a matrix coming out of a 0, I can just replace that with a 0 again. There's a 0 missing here. So A is injective. And then the rest follows. Okay, then you have the bizarre argument for the fact that the inverse works in the other way. Okay, so again, it's not it's just a cute little fact about how to think of an inverse matrix using string diagrams, and we've actually been using theorems like this. I'll tell you about some work that I'm doing at the moment at the end. So I mean, of course, it's true that I haven't really done very much with linear algebra, but I claim that similar stories can be told for other parts of linear algebra. So in particular, decompositions of matrices, things like eigenvalues and eigenspaces, even determinants. And the cool thing that I think about doing this is that we're kind of redoing all this well-known maths, but without using things like vector spaces, bases, linear dependence, independence, spans of vector lists, dimensions, all of these things that we've kind of built up that are taught as standard linear algebra don't appear when you use this language, right? It's something else. So I'm quite attracted by this sort of not needing to use any of these notions. And of course, much of this work is in progress, and this is what I plan to do on the blog, kind of as a fun thing to eventually come up with enough material that you could basically teach this as a linear algebra course to a first-year undergrad. And I have some. Maybe I should save the philosophical remarks until the end. Okay, good. So we have plenty of time for the maybe the most worked out application of these string diagrams, which is to talk about signal flow graphs.
Can I ask you a question?
Yes.
About the linear algebra story. So,
yeah.
Maybe this follows really from what you've said, but if so, I can just explain that. If you've got two linear maps that are presented in this system, how can you test if they're the same? Is this decidable?
Good question. Yes. So
you could just turn. It must be decidable because you could just turn them into actual linear maps and check if they're the same. But the point is to stay within.
So decidability is something that I really haven't thought about enough. So for bimonoids and Hopf monoids, the story I gave you is the story with distributive laws, but you can also do it with rewriting. So you have normal form, so everything obviously is decidable. For the interacting Hopf monoids, the story is a little bit more murky. So we talked a little bit with Alex about this, about coming up with rewriting that terminates in various special cases. I don't know about the general case, but it's totally. I mean, of course, it's an obvious question to ask.
But it's not confluent then the system that you presented. You can't say that the confluent rewrite system easily.
I don't know of one. No. I mean, it's really difficult to know what a normal form of a space should be, right? I mean. There's no such thing as the most efficient. I mean, there's different bases you can come up with, and there's different sets of equations, right? So, what should the normal form be?
So, is this how bases might get back into the picture? So, if you do choose a base, maybe you can't find a nice algorithm.
Perhaps, yes. I'm going to try and stay. I'm going to try and stay away from it for as long as I can. But you're right. I mean, at some point. at some point these questions will need to be answered. I mean, maybe I should say now why do I think this is important?
Question?
Yeah.
So you're suggesting that maybe we should start teaching linear algebra to first year graduate in this way?
Yes.
But one of the things they learn in the first year, at least where I've been teaching, is how to solve linear systems of linear equations. And I don't know the English word for this, but it's wiping a matrix where you multiply columns with each other. How do you call this in English?
Gaussian elimination. Is it Gaussian elimination?
Oh, it goes in elimination. Yeah. Can you also do that with diagrams? Is there an intuitive way of doing that? Because that's a very fundamental operation.
So, I don't have a satisfactory story, and by satisfactory I mean I can redo Gaussian elimination as it's done on matrices diagrammatically, and I can prove that it's the same. I mean, maybe it is kind of cute because normally we teach students, okay, we have these operations, these basic operations on matrices, and they correspond to things called elementary matrices. So elementary matrices are quite intuitive as diagrams. I think you actually have a diagram that takes a row, copies it, and adds it to some other row. So there's something cute here, but I don't know if I have any very deep insights that are very different to what's typically done.
Yeah, but it could already be that your graphical formula isn't out very much.
Well, I find it almost. I mean, so the way we normally teach linear algebra to students is we write down the formula for multiplying matrices. Where does this formula come from? I mean, everyone learns it in first year, right? So we don't question it, but it's actually very difficult to explain. I mean, I have to teach linear algebra to first year students, and it takes them quite a bit of time to get it. And they get it by memorizing, these kinds of algorithms in their head. But this is not the way we should teach maths. We shouldn't teach maths, by telling people to memorize algorithms. It's something. So I think that the story here is much nicer because it's about how copying interacts with adding. Yeah.
You can tell them it's nicely position.
What about multiplication of matrices? If you have two linear maps in basis for your vector spaces, you can count these maps as matrices. And matrix multiplication.
It's composition, yes, sure. Yeah, sure. So that would be sort of the way that you get it explained to you in the second year linear algebra course, right? So linear algebra done right. But again, I'm not really happy with this, right? I don't like this idea that here's a vector space, infinite collection of vectors with some action. I mean, this is it's not very satisfactory from a category theory point of view. I think this is not. We should get away from sets, and I think the story here is cool, no? Because it's about these equations tell you how this very sort of basic copy operation interacts with a very basic add operation. And linear algebra, by the way, so maybe I'm getting into my philosophical discussion a bit early. So I think the point about doing this thing in this way is that linear algebra gets applied in all kinds of different ways, in all kinds of different fields, where the connection with the standard, let's define a vector space in this way and a linear map in this way, doesn't really make much sense, right? I mean, in graph theory and in various domains, the same kind of structure can be, or very similar structures can be identified. And I don't know, I mean, I think the string diagrams are kind of more closely connected to reality. And I think, on that note, you should see an example. And this is the best example that we have so far of this phenomenon. Right? So maybe we can continue the philosophical discussion afterwards. Okay, so let's talk about signal flow graphs. So first of all, we're going to slightly generalize. We started with the integers, right? So we've started with Hopf monads. So it's very easy to generalize this to an arbitrary PIDR. And the way we do this is we simply enrich the theory of Hopf monads by adding extra scalars from a PID and ensuring that the PID structure, the PID algebra, is compatible with the string diagrams. So in particular, this is the way we do addition. Identity is just the identity wire. Multiplication is composition, and 0 is the string diagram. So, in the proof, I told you that we want to construct pullbacks and push-outs of matrices. To do this, all we need to really know is that the underlying ring is a PID. So all of this goes through the same way. We get the same equations. So in particular, one thing that's quite interesting is a diagrammatic calculus for spaces over the field of fractions of, let's say, the polynomial ring Qx. Okay, or any other field. I mean, Q is you can start with any field you like. So these are polynomials with one variable, and this is especially interesting because polynomial fractions, so this is a classical sort of nice syntax, right? So it's a nice syntax for many infinite series, and this is known as the theory of generating functions. So we have a very nice compact syntax for infinite data, which is somehow a very computer science concept, right? A generating function. So the way this works formally is that, so why are polynomial fractions useful for describing infinite series? Well, there's an embedding of fields from the field of polynomial fractions to the field of Laurent series. And Laurent series, you can think of them as formal power series that can start sometime in the past, or just as streams that can start sometime in the past. And by in the past, I mean the first term might be x to the minus k in the formal power series, for some k. Okay, you'll see some examples. Okay, so we have a diagrammatic calculus for polynomial fractions, and it turns out that this diagrammatic calculus is very closely related with something called signal flow graphs. And signal flow graphs were this diagrammatical formalism invented by Shannon in the 1940s. It's probably one of the least known papers by Shannon. And that paper was somehow forgotten, and the notion was reinvented by Mason in the 1950s. So in fact, electrical engineers normally call these things Mason diagrams. And it's really a foundational structure of control and signal processing. Maybe it's not quite the notion of automata for control and electrical engineers, but it's a foundational structure in the same way as automata are, in a similar way as automata are to computer scientists. And so this is a useful circular syntax for linear time invariant dynamical systems, and we'll see some examples of how the string diagrams really are very closely related to these gadgets. So let's do the cube with one extra level, right? So now we're doing the cube, but starting with the ring of polynomials. So by essentially doing the same thing as we did before, we obtain the theory of interacting Hopf monoids for this field of polynomial fractions, which gives us the theory, the symmetric model theory of linear relations over this field of polynomial fractions. Okay, now we can sort of build a -1 level by mapping everything to to formal power series and Laurent series, right? So basically, Laurent series is also the field of fraction of formal power series. So I don't really want to spend too much time on this. It's a bit, obviously there's a lot of information here to process, but the thing that I want to point out, the main point of the slide, is that, okay, so the red arrow here is an isomorphism, and it's an isomorphism for the same reason as we've seen before, right? Because essentially we've constructed this theory from simpler theories which were characterizing span and cospan, and all the kind of, the horizontal faces here are push-outs. Now, this lower level, these blue arrows, they're no longer isomorphisms, but they are faithful homomorphisms. Okay, so we have this composite here from this symmetric monoidal theory to the prop of linear relations over Laurent series, and this sort of the symmetric monoidal theory is sound and complete as a theory for this guy, and it's sound and complete because there's a faithful homomorphism of props from it to it. Okay, so we can basically use our theory of interacting Hopf monoids to reason about these infinite series, and I'll show you some cute applications of this. So okay, by the way, I didn't really show the syntactic, the actual generators, but essentially they're exactly the same as before, except now we have an x. We have an extra scalar called x, and we treat it as the indeterminate. Apart from that, it's all the same. Okay, so in particular, we can write down the diagram for the fraction, x over 1 minus x squared. And maybe some people recognize this. This is the generating function for the Fibonacci sequence. Okay, so this diagram, as a linear relation, we can understand it as the one-dimensional space generated by this vector. And when we map it down to Laurent series, well, 1 is just the string 1, 0, 0, 0 forever, and it turns out that this guy here maps to 0, 1, 1, 2, 3, 5, 8, and so forth, right, the Fibonacci sequence. So I underlined the first element because in a Laurent series it's possible to start before sort of time 0. Okay, so we have this, we have diagrams. Here we have spaces over Laurent series, over the field of Laurent series, and we can use our diagrammatic calculus. We can use the string diagrams as a sound and complete theory for this guy, right? So whichever transformations we make graphically will be kind of sound down here, and also if we have two diagrams that denote the same thing, then we should be able to then we can find a way of getting from one to the other by diagrammatical reasoning. Okay, so this brings me to the operational semantics, right? We want to think of these diagrams as actual circuits that compute things. So what we've done in this paper is we've taken the syntax of string diagrams and we actually gave an operational semantics, and this is a very standard sort of way of giving operational semantics to a programming language, which goes back to Gordon Plotkin, standard, structural operational semantics presentation. Maybe with the one sort of exoticism that labels are on both sides of the arrow, because essentially here the labels on the transitions. I'm sorry, maybe it's a bit too small to see from the back, but essentially we want to think of the individual generators as a syntactic term, and we're giving a semantics. And for example here for the copy, right, the basic transition is k, 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 and this is saying that the signal here should be the same as the signal here and the signal here, right? So the label above the arrow tells me what happens on the left-hand side, the label underneath the arrow tells me what happens on the right. And as a result of this transition, I'm not changing states. So in particular, the only thing that happens here that's interesting, well, apart from the way you compose, which is also quite straightforward, is what happens with this extra x indeterminate. So the x indeterminate is the one part of the language that has an interesting operational semantics, because this is where the state comes in. Okay, so basically, we think of the x as a one-space buffer. So at any point it has a state, it remembers a value. So we kind of denote it here with this superscript. This is the current state. And the transition works by basically accepting anything on the left, outputting its current state on the right, and then becoming the thing that it accepted from the left. And the same thing happens over here. Okay, so I don't really want to spend very much time on this. I'm going to give you plenty of examples. But I just want to make the point that this thing is a formal way of giving the semantics, right? So when I start talking about the semantics of actually running these diagrams as circuits, that's all sort of above board, right? I'm not waving my hands. It's generated by this inductive definition here. So let's go for an example. Okay, so this was I hope I was supposed to define this earlier. Let's